Okay. Good afternoon, everyone. Am I audible?
Yes, good afternoon.
Okay. Good afternoon. Good afternoon. So, okay, we will wait for 1 or 2 minutes, then we will start. Okay. Abdul, have you solved the previous two assignments?
Yes, I have solved the two assignments.
Okay. So, if you people are attending the interaction sessions and watch the videos, then I hope you can able to solve the.
Yeah.
Yeah, and it will be helpful for your final exam also. And later on, when we will, work with the codes and algorithms, so these
Uh-huh.
interaction sessions will be more beneficial, like how to, code the second order, first order reliability method, and all other simulation-based techniques. So you will spend more time on coding and all these things. So that
Okay.
will be helpful, and I will be there, no problem. So, okay, we will start, and others will join if any. Okay. So, okay. So today is the third interaction session on reliability based structural design. So this course is instructed by Professor Arunashis Chakraborty, IIT Guwahati, and I am the PMRF TA for interaction sessions. And for every Sunday, 3 to 5 p.m., we generally conduct the interaction session. And during that 2 hours, what we generally do, we quickly go through the concepts related to that particular week. That means we are on third week, so we will discuss the topics related to third weeks, and we will solve assignments, solve tutorials, which will be, helpful to solve your assignments as well as your final exam question papers. And we also solve problems and tutorials on MATLAB. And every session you will get the link to the recording video session and assignments and the MATLAB scripts. Okay, so the third week lecture actually content that module reliability index. So first we will go to that concepts little bit, then we will solve problem related to, uh, that mean value first order second moment method, this, and then we'll further move and see that how to solve tutorials regarding the Cornell's and Hasofer-Lind reliability index. So basically, uh, during the last two interaction sessions, what we have learned, what we have, that concept of random variables and, different variance algebra to find out that moments of the random variable. So we have seen different kind of random variables, discrete and continuous, and also we have seen how to find out the moments of the random variable. So today we will see, how we can incorporate the random variables within the design problem to model the uncertainties more accurately. Okay, so today we will spend some time on first, the concept of reliability. So first, like, think as a perspective of a designer. So every design, when you are designing something, so every design must ensure the three things. Firstly, the safety. We need to ensure the safety and serviceability, as well as we need to, you know uh, we need to satisfy the economy also, otherwise your client will, interact with you. Now, till now, what we have encountered with respect to the design, they all are like in deterministic framework, where we basically, what we do, we make the capacity of the structure or an element, or an, you know element of the structure, that the capacity of this should be greater than demand, and from there we can have the factor of safety, the non-dimensional number, that is nothing but the ratio of capacity and demand. Now if we have some factor of safety which is greater than 1, that means your capacity will be more than demand, and the uncertainties regarding your demand will counteract by this reserve strength, and which we will get from the factor of safety. Now recall, we have different codal provisions for this type of deterministic design approaches. Like we have IS 456 for our RCC design, we have IS 800 for the steel design. Now the problem is when we deal with the deterministic design framework, like if we want to incorporate the randomness which may generate due to the demand, which may come from the external or internal properties, so how we can deal with them, right? Like if we have the capacity and demand plots here, we can see that if we consider, so here let me explain the plot first, just two plots of the capacity and demand. Here the values of the capacity and demands are, you know, uh, given in your x-axis. So we can see the mean value from this curve. The mean value of the demand is almost 25. Like if it is in kilonewton or newton, whatever it is, the unit is not given. Like say for example, we go with the number 25, okay, and the capacity is like beyond 35. So that means if we stick to the deterministic framework, obviously the design will be safe, because your capacity, mu of capacity, is greater than your mean of your demand. So we will get an additional reserve strength which will encounter the uncertainties related to your demand. Now, look at the case where here, if we see here these two plots of capacity and demand, so we can see one thing clearly, that some portions, like in deterministic design, what we have done, that we take the mean value of this capacity and demand. Now see this point here, if my capacity and demands are random and that can take any value. So now here look at the point here where we can see the capacity is less than your demand. That means, okay, due to uh, the uncertainties, you know, related to your capacity and demand, we can have some failure probabilities or failure zones. Like here we can see that this area, this area is a critical area where the capacity is less than demand. That means the failure can occur if the capacity and the demand will take these values of this portion. Now, how to deal with that problem when this type of randomness will occur in capacity or demand both? I will tell you what is capacity and demand and how to formulate the limit state in a minute. So for this case, the deterministic framework will not give you the proper, uh, design outcomes. So we need to go to reliability based framework, where actually reliability based framework gives us like how to deal with that uncertainties, or how to, you know uh, more precisely how to model these uncertainties within our limit state. So in reliability based structural design, the failure criteria or the reliability actually defined with respect to the probability of failure. Now if we want to define the reliability, that will be nothing but 1 minus probability of failure. Now if we want to, provide a formal definition of reliability, so it is nothing but the probability of an item performing its intended function over a given period of time and under certain operation conditions. Now if we have this kind of problem, so how we can formulate the limit state, how we can model that uncertainties, and how we can get the probability of failure, so that we can get the reliability, that will be our main question, our main task. So today we will, see one of the reliability method, how we can find out the probability of failure and reliability associated with the structure. So here there in if you go went through your video lectures, so if you see that the course instructor had already explained the level of, that safety checking and risk assessment format. So first, level 1 actually deals with the deterministic one, like whatever we have learned up to uh, grad undergrad courses. So we have seen that we have some codal provision, and according to we need to design. In general, what we do, we generally overestimate the load and underestimate the capacity. Like recall that 1.5 for dead load and live load combination. That means we are overestimating it. And for the factor of safety for material, if we consider in limit state and for the concrete 1.5, so we just reduce the capacity and increase the demand, so that the uncertainties related to the demand will be counteracted by the reserve strength which is coming from the factor of safety. Now in level 2 reliability, what we generally do, we formulate some limit state function based on some elements. So we break down the structure in element level or different component level. Then we formulate the limit state, and in limit state, we model the uncertainties and solve for the probability of failure, and we get the reliability. And in the third level of safety checking format, it's the precise modeling. As a whole, we model the structure like AFE modeling or sort of different kind of modeling. So we will see later on this course. Okay, so first what we need to understand is the concept of limit state, and then we can further move that how we can use the limit state to quantify the uncertainties and to find out the reliability and probability of failure. So so let's consider this steel beam, okay, here, and it has a cross section. So from the cross section we have these two parameters. I, we have from the cross section we have I, from the material properties we have E and L, and external load P is applied on the free end. So what will happen? The beam will undergo deflection. Now, if we want to design with respect to serviceability criteria, so the serviceability limit state says the maximum allowable deflection should be L by 325. That means that L by 325 is nothing but your capacity. Now, what will be the demand? Due to that external load, what will be the maximum deflection at the free end? It's PL cube by 3I. So this is your demand. Now, how to formulate the limit state? Limit state actually is nothing but it's the capacity minus demand and make it equals to 0. So your limit state, that means Gx content the capacity and demand both information, right? C minus D is equals to 0. So here for this beam, for this problem, for this cantilever beam problem, we can easily formulate the limit state function, right? It's like capacity. We are like for this case, we have considered that we are designing with respect to the limit state of serviceability. So for limit state of serviceability, the maximum limit is like that, and this is your demand. Now here, when we have formulated this limit state, now look into the parameters like P. It can be a random variable following some distributions. So randomness may be there. Now L can be a deterministic quantity. Generally L is the deterministic quantity. EI, again we can incorporate randomness in here. Now with respect to that limit state, how we can define the failure for a design. So if I draw the limit state in a plane, so here you can see the limit state is drawn in a plane. So that means the points which lying beyond these points, they all considered as failure, because on that side the limit state value Gx is less than 0. That means your demand is greater than capacity. So obviously if the demand is greater than capacity, that means the failure will occur. Now to simplify it, I have drawn the limit state, the PDF of the limit state. So here you can see this is the 0 point, right? So Gx is equals to 0, that is our limit state. If Gx is greater than 0, that means if Gx is greater than 0, what will happen? Your capacity is more than your demand. That means our design is safe. So all the portion, right hand side of the 0 will give us the reliability, while the part up to the 0 point will give us the probability of failure. That means if we have a limit state, then we can define, okay, the limit state value, if it exceed or greater than that desired point of failure value, then we can say the design is safe. And on the other hand, if the limit state values are less than 0, that means your demand is more than the capacity. So these points will give you, or these parts will give you, the probability of failure. Now if we can calculate the probability of failure, now look at this distribution, look at this distribution. Okay, so up to this point, if we integrate the PDF up to this point, right, so that will give me the probability of failure. So what do we need to do? First, we need to have the limit state, then we need to have, the PDF of the limit state, or the method how to define the failure probability through the limit state function, right? That is our main goal. And how we can solve it, that we will see in a minute. Okay, so now think about it. We have the limit state, g of x is equals to capacity minus demand. Now, if we can find out the first two moments of the limit state, so let's see if we can have the two moments of the limit state, can we define the failure probability or can we define the reliability? So first task is that, okay, let's see if we have the two moments we have already, came to know about the moments of the random variables, right? So recall that variance algebra, where, you know we have, if we have a function of random variables, then we can expand it with respect, with the help of Taylor series. So if we have the limit state, so first step is we have the limit state, that is c minus d is equals to 0. Now what our task is, to expand the limit state with respect to some point. Say for example, for x star point, we expand the limit state with help of the Taylor series expansion. Now, if we consider that the reference point is mean, if we consider that the mean is the reference point for the random variables, that may not be the case, but for example, for first case, let's take that mean is the reference point of our case. So if the mean is the reference point, we can find out the mean of the limit state function as nothing but e of gx, that means g of that mu points or mean points. And if we truncate the series up to the first order, so we will get the sigma square also. So we spend time on that variance of algebra, how to find out two moments. So here we can also see that, okay, from the variance of algebra and using Taylor series expansion, considering the mean as a reference point, we can have the two moments, first two moments. Okay, right. Now, if we have the first two moments, can we get the probability of failure or reliability? That is our first question. So we have that first two moments from the Taylor series expansion. Now let's see if we can define the probability of failure from this or not. Let's consider that our capacity and demand both will follow normal distribution. For now, let's consider this follows the normal distribution. So we know that normal distribution has two parameters, mean and sigma. So capacity, it's nothing but it follows normal distribution with mean mu c and standard deviation sigma c. Likewise, the demand is of follow that. Now, so we have the gx is equals to c minus d. So if capacity and demand both follows normal distribution, obviously your limit state function will follow normal distribution. It's the basic property of the normal distribution or normal random variables. Okay, so now we have that limit state. When we call a case failure, when your gx will be less than 0, then we can call it a failure. So once we have the limit state function, from variance of algebra, we can calculate the mean value of the limit state function. So what will be the mean value of the limit state function? It's a linear function, so it will be nothing but mu c minus mu d. What will be the variance? Again, it's a linear function. If there is no correlation, then it will simply sigma c square plus sigma d square. And if there is correlation is there, and if the correlation coefficient is also provided, this is correlation coefficient is provided, so we can again get the value of variance from the variance of algebra. Now recall what was the uh, PDF expression for PDF of normal distribution, that is nothing but 1 by under root of twice pi sigma g e to the power minus half g minus mu g by sigma g the square. Now our failure region is up to that. If we have the PDF of the limit state function, now how we can define the failure? It's nothing but the probability of failure will be, you need to calculate the area under this PDF up to the portion 0. That means minus infinity to 0. Why minus infinity? The domain of that standard normal distribution is minus infinity to plus infinity. So minus infinity to that, you just need to integrate your limit state function, right? So we have also we also came to know about the standard normal variate. Like we can bypass this integration using the standard normal table. How? Using the standard normal variate phi of g minus mu g by sigma g. Yes or no? Now the value g here taking is 0. So we can further simplify it like phi of minus mu g by sigma g. Yes or no? So now if we move further, that we have seen that if we have two uh, distributions, and from the capacity and demand, if we can find out the mean and standard deviation, that means the first two moments of the random variable, so we can define the probability of failure through that two parameters. So here the ratio of the mu g and sigma g is called the Cornell's reliability index. Actually, in 1969, Sir James Cornell has actually proposed that or find out this reliability index. So first thing what we have here need to do, first we need to define the limit state function. We need to calculate the first two moments, and then if we get the first two moments, we can have some non-dimensional number, we call it Cornell's reliability index, and which is nothing but the ratio of the mean of the limit state divided by standard deviation of the limit state. That means the ratio of the first two moments of the limit state. First moment about origin, that is the mean, and it is the second central moment, right? We already have discussed on this on the last class. So once we have that non-dimensional number beta, we can actually quantify the probability of failure like this. Probability of failure will be nothing but the standard normal variate of phi of minus beta. Now if we can calculate the beta, phi of beta, we can easily get it from the standard normal table, or we can use calculator or any other thing to find out the probability of failure. Now once the probability of failure we get, we can easily find it out what will be the reliability. So reliability is nothing but 1 minus probability of failure. So this non-dimensional number which defines the probability of failure, and this is the ratio between your mean of the limit state and standard deviation of the limit state function, we call it Cornell's reliability index. And the method here, we have derived the mean and standard deviation from the first order Taylor expansion, and here the first two moments are considered. So this method of finding out the probability and reliability is called mean value first order second moment. Now why mean value first order second moment? Here we have seen that that MVFOSM, right? The topic of that reliability method, MVFOSM. Mean value first order second moment. Why mean value? Because we have considered the mean as a reference point, but not always the case. We will see lack of inference problem regarding that MVFOSM. Now first order, because we go up to the first order and we truncate the series at first order and take the second moment from there. So let's quickly solve some examples regarding how we can actually calculate the probability of failure based on this first MBFOSM method, and how to calculate the Cornell's reliability index or the reliability index from here. Okay. So up to this, any doubts what we are trying to do today's lecture, you can ask me, or we can solve some problems. So today we will solve step by step. Okay. Yeah, Abud.
Yeah, no doubts. Tell me.
Okay. So let's solve problems. Okay. And you also solve the problems simultaneously so that these things get clear. Okay. So first tutorial, the axial load carrying capacity of a column is given. So that defines your capacity, and that capacity follows normal distribution with mean 1000 kilonewton and standard deviation 200 kilonewton. Now the column is subjected to an external load, this is demand, also follows normal distribution with mean 700 kilonewton and standard deviation 300 kilonewton. Now calculate the reliability of the column considering C and D are statistically independent. Now statistically independence we have already seen. If they are statistically independent, there will be no correlation. In short, we can multiply the probabilities. And also we have seen that stochastic independence and what are the criteria to satisfy the stochastic independence, all this. Okay, so first step to solve this kind of problem or to handle this kind of problem, first you need to define the limit state. So here the limit state is capacity minus demand. Our capacity and demand is given. So what do we need to find here next? Just find out the mean of the limit state. So it's a linear function. So mean, what will be the mean value of the limit state? Mu g will be nothing but your mu c minus mu d. And the mean value of capacity and demand is already given. How much? 1000 kilonewton minus 700 kilonewton. That means 300 kilonewton. Right? Now what do we need to find it out? We need to find out the second central moment. That means your variance. So variance of the limit state, that means sigma square, or you can directly write it down standard deviation and under root of the right hand side portion. So it's again in linear function. So what will be that? Mu c square plus mu d square. That means we have the values, sorry, sigma c square,
Sigma.
yeah, and sigma d square, right? So we have the sigma values 200 square plus 300 square. So how much the value you are getting? Tell me. Just give me the sigma value. Sigma will be under root of that 300 plus 200 square. So just calculate it. Under root of 300 square. How much is coming?
360.55.
Okay. 360.55. After you getting the root, or before the getting the root?
After getting the.
Okay. So give me the value of sigma only. What will be the
Uh,
value of sigma?
just, it is coming out to be 360.55.
Okay. 360.55. Right. 100 square plus 300 square. So we have mu and sigma both. Now what do we need to do? We need to find out the beta reliability index. So what will be the beta value here? Calculate it. It's nothing but your mu g by sigma g, right?
Yeah,
So 300 divided by 360.55, and it
point
is
eight
0.83.
83.
Now you can find out the probability of failure. Probability of failure will be nothing but phi of minus beta. That means phi of minus 0.83. Now, from where you can get the value? Look for the standard normal table, or you can directly solve it through the calculator. So let's go to the standard normal table, as we don't have a calculator within us while the final exam. So we have to rely on the standard normal values. So standard normal values will be given. So we need to look for 0.83 minus 0.83, right? So here minus 0.8, and we need to go up to the point here, 0.83. So the value is nothing but how much? 0.2033, right? Yeah. So from the standard normal table, we are getting the value as 0.2033. 0.2033. Now we can calculate the reliability. What will be the reliability associated with it? Reliability of this column, 1 minus probability of failure. So 1 minus this will give you the value. So 1 minus 0.2033. So that is your reliability for the problem. So 1 minus 0.2033. That comes as 0.7967. Okay. So by this way, we can find out the reliability index as well as the probability of failure and the associated reliability with it. Clear? Any doubt? So we will solve more problems, more complex problems. So let's move to next problem where we will solve these values. So here I have added the uh, thing like 0.832 was coming. So from the calculator directly it's coming as 0.27. Now from the standard normal table also give our 0. Zero 03. So you can directly calculate from the calculator or you can use the standard normal table. But the values will be provided to you for the exam purpose and for the assignment purpose. You just go stick to that values. Okay. Now let's solve this problem. This problem is taken from your uh, lecture videos, and this is also given on the book Ranganathan as well. So here we see that one cantilever beam is there. Now one point load is acting at the free end. So first, what we need to do, that we need to design the beam with respect to limit state of serviceability, and the limit state of serviceability given as that. So the limit state function g of x is given here, L by 325 PL cube by 3 here, where look at here, where there are three parameters which are random in nature. The load P, which follows the normal distribution with mean 60,000 and standard deviation 9,000. L, it's a deterministic quantity. Sorry, it's also follows that random variable, and it's has that 2500 length, and the standard deviation as 125, and E also uh, follows that normal distribution with mean this and standard deviation this. So to solve this problem, first what we need to do, we have the limit state. Our main goal is to find out first that what will be the mean of this limit state. So first thing, we need to find out the mean of the limit state. So what will be the mean value of this limit state? Mu g will be nothing but you need to put all the mean values. So mu of L divided by 325 minus mu of P into mu of L cube divided by 3 multiplied by mu of E into mu of I. So I is a deterministic quantity. Here the values are provided. So now if you put all these values here, like mu of L, what was the mu of L? 2500. So 2500 divided by 325 minus P. The P value is given 60,000. L 2500 cube, and all these values I put it here, and the mu g value, if you calculate it, you can recheck the calculation, I may be wrong. So the value of mu is coming as 3.11. That is the mean value of the limit state. Now the limit state is formulated based on the limit state of serviceability criteria. Now what we need to find it out? We need to find it out the variance of the limit state. Now to find out the variance of the limit state, we need to use the variance of algebra. Now here we have like a nonlinear function. So for the nonlinear function, what do we know? First, we need to differentiate that limit state with respect to the random variables, and then only we can find out the variance of the limit state using like this formula here. Okay, so let's see how we can solve this problem. So we have here three random variables, P, L, and E precisely. So first, just differentiate with respect to P. What we will get? So simple differentiation, we will get minus L cube by 3I. Then with respect to L and with respect to E. Now, once we have all these values, I just simplify these values here, put all these values. So the differentiation values we will have in our hand. Now, once we have the differentiation, we can easily get the standard deviation or variance value from here. How? So sigma g square will be nothing but del g by del p, our first variable, truncated at mu point, multiplied by sigma p square plus del g by del l square into sigma l square, and del g by del e square plus sigma e square. Now here for this example, there was no correlation between any of the variables. If there was any correlation, then we need to also encounter that or consider that correlation within our problem. Yes,
Yeah, actually, I have a question in
yeah,
the next slide. Can you please move the slide? The formula for sigma square, actually. Yeah,
yeah,
sigma square G.
yeah,
We are using sigma square P, sigma square L, and sigma square E in each of the
yeah,
terms.
yeah.
But does it appear in the formula that we just saw in the previous slides?
Yeah, that
I
was actually for the correlation formula. Actually, if you watch the video of the previous class where we have solved that problems related to correlation coefficients, there this thing will
yeah,
come.
this one.
Like here also that will come, like summation of first thing, we first variable with respect to this value,
Yeah,
and again
yeah.
if we consider the related to that value and the covariance. What is the covariance means? It's nothing but,
It is one right now.
yeah,
Yeah, I
and
got it.
that if there is no correlation coefficient, so it will eventually become your sigma square value. So sigma square of that multiplied by this value plus, again you
Okay,
need to
okay,
go
okay.
for the summations. That's
Got it.
how
Got
you
it.
can.
Thank you.
Yeah.
Uh,
And if there was correlation coefficient, that square term will not come, right? The square term is basically come from this covariance. If there is no correlation coefficient, the covariance will become your variance. Clear?
Thank you.
Okay, so let's solve this problem. But I suggest that you should go to that videos where we have solved that problem related to this correlation coefficients. So we will see in a minute also. So if you put all these values here, you will get that your standard deviation will come as 0.7843. Clear? Now we have the mu value. Mu of g is equals to like 3.1146, and sigma g is equals to 0.7843. Now you can calculate the beta value. It's nothing but that ratio, 3.9712. Now once we have the beta value, we can calculate the PF, probability of failure. Probability of failure will be nothing but phi of minus 3.9712. Now check and give me the value if you are getting this value from using calculator or not. Because in your standard normal table, the value of 3.97 is not provided there. Like if we go to the standard normal table, like 3.4 is the last value which is provided. Like behind that we will have less probability of failure. That's why. But if this kind of problems will come, then the values will be provided to you. Now use your calculator and give me the value. Do you know how to use the calculator to find out that phi value, Abdul?
Not particularly. I use MATLAB for it usually.
Yeah, you can use MATLAB. Obviously, MATLAB is well and good. But if you have a do you have Kelsey with you?
Yeah, I do have it right now.
Okay, which one?
FX Casio FX991.
991. Now,
Yeah,
so
yeah.
just go to first setup mode.
Uh huh.
Yeah.
Fine.
So in mode setup, just you need to go for statistics. Three option
Yeah.
three is there. Like
Yes.
that. then go just close that
AC, fine.
AC, then uh, go to SIP and that your stat one.
Shift and stat one, yeah.
Yeah, and you will find that distributions are there on the seventh number.
Uh, it is on my fifth number distribution, yeah.
Yeah, whatever it is. Now that P, R, Q, these values are coming, right?
True, yeah.
Yeah. So one P, just put one,
One.
one. Now
Uh-huh.
put the P value. So here the phi value is minus
Uh,
3.9712, right?
3.9712, yeah.
Yeah. How much value is getting?
3.5772 into 10 raised to minus 5.
Yeah, right. So by this way, you can directly calculate it. I don't know. Or MATLAB is well and good, but you cannot run MATLAB all the time.
I didn't know it. Thank you. Thank you.
Okay, so by this way, you can easily calculate it and check whether your results are giving uh, right, or you have any doubts. So you can check it corresponding. Okay, so now give me what is the probability reliability here. So we have bigger reliability. Like our probability of failure is very less, right? That's why we will have higher level of probability for this case. Now if within that problem, like if that ei or many other parameters, here we have considered the higher values of, so for sectional parameters and lower values of load, that why that will be well within that limit. That's why our design is safe. Now if we have some random variables which will take more values and giving us the higher probability of failure, then we need to check the cross section and do the design accordingly. Clear? Great. So now let's solve another problem. So we will just solve problems today regarding that, so that your assignments will get solved. So this is another problem. So what that problem says, the RCC section, uh, so this figure is not here. So okay, no problem. The B width is given. The width is follows normal distribution. Okay, with mean 400 and standard deviation 4. Also, the depth is follows normal distribution with mean 700 and standard deviation as 4. Now, evaluate the first two moments of the moment of resistance of the section. Also determine the reliability of the applied bending moment if the applied bending moment is 700 kilonewton meter. Great. So, what that question says, you have a, you know, RCC section where your B width is given, your effective depth is also given. You need to find out the moment of resistance. So moment of resistance of a RCC beam, if we consider the concrete failure, just recall your IS 456 will give you this formula. Page number 96 you will have on appendix D. If we consider the concrete failure as a failure criteria, right? For the unreinforced section, for the balance section. Now here we have that Fe410 steel. So write it down. The question is incomplete. The steel is Fe415 grade. So if we, for the Fe415 grade, we have like XU by D value, particularly on page number 69, recall, right? So from here, we can have the moment of resistance for the Fe415 steel, that is 0.138 FCK BD square. Now this is your limit state, G of X for this case. Now we can find out the mean of this limit state. It will nothing but, here we have that two variables, FCK, we know the value. Is it given to you FCK? No. So M20 concrete is also M25 concrete, you need to consider. Okay. So steel, grade of steel and grade of concrete, just incorporate into the question. So grade of concrete is 25 and grade of steel is, okay, say for example 450, 4 and 5, 415. So here we can easily find it out that mean value comes as 676.2. You just need to put all the mean values here. Now what we need to do to find out the variance, we need to differentiate with do differentiate that gx, that means our limit state function with respect to the random variable. So here we have two random variables. One is b, another is d. So just differentiate it. You will get that when we differentiate with respect to b, we will get 0.138 FCK BD square, like only we have b, and here just 2 BD. Now again put the equation here. We have the equation for it, like it's there is no correlation is there, so directly it will come as like this. So if you calculate these values, so here the standard deviation of the moment of resistance, the standard deviation of the moment of resistance comes as 13.4, right? So now think about it. We have like b that follows normal distribution, we have d that follows also normal distribution. We have found out g of x, that means our limit state function. Now for the limit state function, we have found out that the mean of the limit state is that, and standard deviation of the limit state is that. Now the question asks, if the applied bending moment is 700 kilonewton, determine the reliability. So if I want to plot that g of x, okay, now we cannot use the MATLAB right now, otherwise I can plot it into MATLAB. So for example, we can now visualize the things here, like our mean value is somewhere here, and that gives that 676.2 kilonewton meter, and we have a normal distribution, that means we have a bell-shaped curve, right? And the standard deviation also we have found out. Now 676.2 is the mean value. We need to find out the reliability with respect to the bending moment 700 kilonewton. So for example, here the point 700 kilonewton will lie. Clear? So what will be the reliability portion? Obviously this part, because when the value of applied bending moment will greater than that 700 kilonewton, we will get the failure region. So for this problem, what we need to do? We just need to integrate this limit state function up to the our failure criteria. That means we can easily have it from the standard normal table. So phi of 700 minus 676.2 divided by 13.42. So that comes as phi of 1.7735. And what is the value of phi of 1.77? Just quickly check and tell me. It will give you higher reliability, right? The probability of failure will be very less. Look at the reliability. Check the value if it is correct or not, because the reliability is so high, 0.96, right? That means the probability of failure will be like tends to 0. Is the value is correct? Just cross check and tell me.
Yeah, the value is correct.
Yeah. Now, if we want to solve it from the beta will give you directly one value. Like check it if you want to calculate it beta from beta, like beta is nothing but mu g by sigma g. So that value will come so big that will give you, you know, uh, reliability as 1. So for this type of problem, if the point of failure is defined, you need to figure it out how you can going to solve it. Like this problem, we do not need to go for reliability based design. It's already safe, right? So much moment of resistance we have already encountered, like 0.36 FCK BD square. Already in that, the factor of safety for concrete is also considered, right? Otherwise we can have the 0.36 value. That's why the reliability is so high for the case. Get it? Yeah.
Yeah, I'm sorry, but I have a question regarding this problem
Yeah.
number three. So
Yeah.
the
Yeah.
issue is, how have we defined g of x in this case? Since we understood that g of x is equal to c minus d.
Yeah, C minus D. But here in your problem, either the capacity or nor your demands are defined, right?
Okay. Yeah.
So this moment of resistance we are getting from our IS 456, because in your problem says the moment of resistance of the section. What will be the moment of resistance? You need to go back to your RCC. How you
Uh,
can find out the moment of resistance? So this actually moment of resistance with respect to concrete failure. There are moment of resistance, like if we consider the steel failure, so there will be like different moment of resistance. So this is like moment of resistance directly says consider this as a moment of resistance. Okay, so this is your limit state function.
Okay.
And like based on this function we have defined the reliability and probabilities. Clear?
Okay. Okay.
Okay. Like here, neither the demand and capacities are defined. So if you want to actually define the capacity and demand, so if you need to go to that moment of resistance portion where you need to find out the internal stresses due to concrete, then you need to incorporate the factor of safety from that characteristic curve of the concrete. So all these things. Okay, clear? Now let's solve one more problem, one or two more problems. So okay, here I have added a simple problem regarding your covariance and correlation coefficients like this. So if we have two loads, P1 and P2 applied on a beam, the mean of P1 and P2 are given. Say for example, we have a beam, P1 and P2 are given. Now the mean of P1 and mean of P2 also given. And question says they are correlated with a correlation coefficient is equals to 0.7. Now find out the covariance. So from the variance of algebra, what we can conclude that correlation coefficients between two random variable is nothing but the covariance between them divided by standard deviation of P1, standard deviation of P2. Now you have the rho value. So you can find out the covariance of P1, P2 is equals to nothing but rho 1 2 into sigma P1, sigma P. Okay. So just put all these values. What is coming? The correlation coefficient between that two is given as 0.7. Now the mean value, the standard deviation of P1 is also given. What was the standard deviation of P1? Variance of P1 is given as like 4. So standard deviation is nothing but the variance under root of the variance. So 2 and 2.24. Why 2.24? It's 2.25. Okay, just make it correct. So you will get the value as 3.136. Clear? So what was the variance formula? Variance is equals to E of x minus mu. That means your second central moment. Okay. Now covariance, what is that covariance thing means? Covariance means is nothing but E of the two random variable, that x1 how much is differed from mu and x2 that how much differed from mu. Testing. And if there is correlation coefficients, what that correlation coefficients means, it will tell us how that two random variable or how that two datas are correlated to each other. Clear? Okay. 2.24, right? So is the value is coming 3.136? Check it. Awul.
Yeah, that is it.
Okay. So now let's solve another problem. Here, what is said, a simply supported beam. Okay, simply supported beam. Now, you people solve this problem and give me the answer. A simply supported beam of length 4 meter is subjected to a self weight of UDL type. O diya hua hai Q1 is equals to this, and this follows the normal distribution with mean this and standard deviation this throughout the beam. Okay. So we have a beam, simply supported beam, and one UDL due to the self weight. One UDL due to the self weight is coming, right? And the value that is defined as Q1, and it follows normal distribution with mean this and standard deviation this. Great. And now we have throughout the beam and a live load of point load. Okay, live load is given as a point load at a mid span. So we have also another load Q2, which also follows normal distribution with mean and standard deviation. Great. Now the flexural resisting moment capacity of the beam is C. Okay, resisting capacity is given here. Okay, that is C, and that follows normal distribution of this. Calculate the reliability index using MVFOSM against the limit state of collapse in flexure. Consider the limit state equation as C minus D. Great. Now we will see in a minute why these things are, actually that the format of the limit state is given, because in mean value first order second moment method we will see that if we change the format of the limit state, eventually the answer of beta will change, and that we call the lack of invariance problem. We will see in a minute. So we need to formulate the limit state as per this format. Okay, so what we have a beam, simply supported beam of length L, and where one UDL and one point load is acting, and their values are also provided. So what will be the maximum moment for this scenario? Moment for the Q1 load, obviously the maximum moment due to that load will be Q1 L square by 8, and that will occur at the midpoint. Also for the for the point load, we will have that much of moment at the center point. So this is the applied moment. If you solve it, you will get 2q1 plus q2. That means this is our, what is that? This is our demand. Yes or no? Due
Yes.
to the applied load, whatever moment we generating within that beam, that is the demand. So we have the demand equation, and that is says that 2q1 plus q2. Now capacity,
How will it change to Q1 and Q2? The L will remain there, no? If we solve it.
yeah, L value, I think side L value is given, otherwise we
Ah, yeah,
cannot
4
actually.
meter. Okay, okay, fine, fine. Okay,
Yeah,
got it.
it's a deterministic value. So just put all these values in this and check whether this thing is coming or not. Okay, we just need to check it. So Q1 value already given, 500 divided multiplied by L, that means 4 square divided by 8 plus what is the Q2? 5000 square, 5000 into 4 square divided by 4. Not 4 square, it will be 4. So check and tell me if you are getting that value or not. Don't need to provide that Q value, just simplify it with respect to L. Just we will solve the Q later. We are getting that to Q1 or Q2 or
Yeah,
not?
we are getting it.
So this is our demand. Capacity is already said that the resistance capacity follows normal distribution, where the mean is given as 1000, 10,000, and standard deviation is given 1000 Newton m. Okay. So now we can formulate the limit state function. Yes or no? So the limit state function g of x will be nothing but capacity minus demand. So capacity is, I have denoted with R, or the resistance, internal resistance, R minus, this is your demand. This is your limit state function. G of x is equals to R minus 2q1 plus q2. Clear?
Mm.
Now, can you find out the mu g from here?
Yes.
Find it out and tell me the value. What will be the value of mu g?
15,000.
15,000. 15,000 what? Newton?
Kilometer. Okay, it is in newtons.
Newton.
Uh,
This is Newton meter. Newton meter, we are dealing with the moment, so Newton meter will be there, right?
Newton meter.
Yeah. So this is your mu g. Now quickly find out the sigma g. Calculate it. There is no correlation. It's a simple linear formula. Just find it out the sigma g value.
1500.87.
1500.87.
87. Yeah.
How you can find it out?
Uh, I've simply used the formula.
Like what formula?
Dow G by dow X1 kind of.
Yeah,
By
that.
differentiating each of the random variable.
The elements, then the whole square and sigma square. You just need
Yeah.
to multiply it. So, okay, let's see we are getting or not. So these values are already provided. We can have the mu g, that means mu r minus this. So 5 kilonewton meter. So I have converted into kilonewton meter. It
Okay.
will simplify the, or you can stick to Newton meter also. But at the end you should have this result.
Okay. So I'll have to recheck my
Yes,
results.
check it where you have missed the calculation, or maybe I may miss the calculation. So like the values are given here. So let's go to the slides. Okay, 500, 5,000, and 11,000. Great. If we convert them here, zero point 0.5 Newton. Newton will be in bigger. Just check it and tell me if you are getting that value or not. Yeah, Newton per meter is given. So already this is Newton. That means you convert it into kilonewton, you will have zero point 0.5. It's okay. 5,000, if you converted into that here, okay, 5 is there, right? No problem is there, and mu are 11,000. Okay, no problem with that calculation, right? 11 minus 2 into zero point 0.5 minus 5. So it will give you, let me cross check the calculation again. 11 minus 2 into 0 0.5 minus 5. Yeah.
Okay. Okay. I've missed out the last minus u2. I've
Okay.
used plus over there.
So either you will get 5 kilonewton meter or 5 into 10 cube Newton meter.
Mm-hmm.
Whatever.
Fine.
Now calculate the variance of G. Just you need to differentiate with respect to R first, Q1, Q2. There is no correlation. So if I differentiate with respect to R, I will get 1. If I differentiate with respect to Q1, I will get minus 2. If I differentiate this with respect to Q2, I will get minus 1. It's very simple. So variance of G, just put it there. This square minus 1 square give you 1. Sigma R already we have like 1. Now here del G by del Q, that is your minus 2. That means you need to square it, and Q1 sigma Q1 value, sigma Q1 sigma Q1. Yes, this value is provided. And the third one, for the third one also minus 1 square and 2 sigma Q2 square is also provided. So if you calculate them, you will get the variance as 3.2516. Are you getting?
Yeah.
So ultimately we have the standard deviation value as 1.8 kilonewton meter. Now calculate the reliability index beta. Is nothing but mu g by sigma g, and this is coming as 2.77. Now give me the probability of failure for this case, and give me the value, probability of failure and also reliability. So in a question, if that asks the what will be the range, so carefully see the range, in which range your answer will lie, and accordingly you will select the correct answer. Get my point? What I am trying to say? Now tell me what will be the probability of failure for this case? Phi of minus beta.
It is coming out to be 2.73 into 10 raised power minus 3.
2.73 into 10 to the power minus 3. Very good. Yeah. I am also getting the same answer, 2.73 into 10 to the power minus 3. That means your reliability will be 1 minus that.
Mm-hmm.
Then we will have higher reliability for that, right? Okay.
Yeah.
So now let's move to Another question. Okay, now let's solve this question. I think this question we will familiar. I think I've seen it somewhere. Okay, let's solve it. A simply supported beam of length 4 meter, again subjected to two concentrated load P1 and P2 at a distance of 1 meter and 3 meter from the left support respectively. Okay, so let's draw it and try to solve it one by one. So we have a simply supported beam and we have two point loads. One is acting here and it is P1 at a distance 1 meter from here, and another load we are having P2 which is acting at a distance 3 meter, and total length of the beam is 4 meter. That means 1 meter and 1 meter apart from its acting. Okay, very good. Then what is given? Given that the mean of the load P1 and mean of the load P2, that two are given, variance are also given. The loads are correlated and the correlation coefficient rho 1 2 is also given. Okay, they both are correlated with a correlation coefficient of 0.55. Now the shear capacity of beam C, that means the shear capacity is defined as the capacity of this condition. So this is given as, okay, the beam can carry up to the shear which follows normal distribution with mean 35 and standard deviation 2. Calculate the reliability index using MVFOSM considering the limit state as C minus D format. Great. So what we need to find out? We know the capacity. So what will be the demand for this case? Tell me what will be the demand for this case? Any idea? Two load conditions are given. Your shear capacity is given. So first you need to find out the maximum shear force which is occurring within that beam. Yes or no? First thing,
Yes.
shear capacity is given. That means you need to find it out the maximum shear force what is generating due to that P1 and P2 load. So let's first quickly go to our SOM thing, then we can understand. So how can you solve it? First we need to use the equation of statics. So fy is equals to 0 if we put, so we will have one formula. Say let's say Ra the reaction from this end and Rb this is the reaction from this end, or we can say that this one is your V2 and this one is your V1, whatever it is. We'll see in a minute. So what we'll have, that P1 plus P2 is equals to nothing but your R1 plus R2. Now take the moment about a clockwise positive and make it to 0. That means this is our one of the equation of static. In a 2D, we have three equations of statics: summation of Fy0, summation of Fx0, and summation of moment about that point 0. Now, if we make it and put all these values, what we will have? Let's check. So we have Rb minus Rb into that value 4 plus P2 into 3 plus P1 into 1 is equals to 0. Yes or no? So Rb is equals to 3 by 4 P2 plus 1 by 4 P1. Can I write it?
Yes.
Rb. That means the reaction at that support. 3 by 4 P2 plus 1 by 4 P1. Now, what will be the value of Ra? Just use this equation. So we'll have reverse of that, right? 1 by 4 P2 plus 3 by 4 P1. Yes or no?
Yes.
Now, out of these two, tell me which one is bigger or which one has the higher value.
RB.
Why Arbi?
Sorry, RA. 30 kilonewtons. Yeah.
Yeah, because the mean value of P is here 30. So obviously we will get that Ra, that means on the left support we will have the maximum shear force. We'll have no doubt. So now we can write it down that okay, shear force at that left support at, you can write it down left. The diagram was not there. Otherwise, you can directly point it out. Okay, uh, RA will be the maximum. So we have now the demand for it, right? Up to this, no problem. How we can find out the demand? Because we need to find out the reliability with respect to shear. So obviously, we need to find out the maximum shear for this case. Otherwise, no logic is there behind it. Now, once we have the demand and capacity both, now we can formulate the gx, because the formation of gx is also given. Like you need to formulate the gx as c, that means capacity minus demand. Now formulate it and tell me what will be the value of mu g for this case. Solve it. Solve it and check whether my answers and your answers are matching or not. If matching, then you can directly go for the answer. Otherwise, we need to, figure it out where the problem is there. Okay. Now tell me, if we formulate the limit state, so we have this as our this is as our demand, and this is our capacity. So G, C minus this value. Now the value of capacity is given. The capacity follows normal distribution with mean 35 and standard deviation. Now I can easily find out the mean of V1, mu C minus, yeah,
Maybe there is a mistake. You have multiplied 0.75 into 20. Should it not be 30?
yeah,
Mu
that
of
will
P.
be 30, right? You are. That will be 30 and that will be 20. That's why I'm asking. Just solve it. So
So
what is coming as
mu will be 2.5 then.
mu will be
2.5.
2.5
Yeah.
kilonewton. Okay, P1 value is 3 kilonewton per meter square. Yeah, 3 is right. And also everything P2, 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 P2 is also right. Great. So 2.5 will be there, right here. You are. And find out the sigma value. The correlation coefficient is already also there. You need to first differentiate with respect to the variables. Then here, look at this part where your correlation coefficients is added as covariance, right? And calculate it and give me the results. I think the variance will be same as I calculated, because here the mean value is not there, only the variance is there. So variance of C, okay, variance of P1 is 4 I have considered. Let's see, 4, 4. Variance of P2 is 4. Yeah, it's okay, fine. I think you will also get this answer. Check it. Like del G by del C, we'll get, if we, differentiate, we'll get 2 plus variance of C, we know, and all the other things. Just put the equation and tell me the values. It's simple.
Same.
Same.
6.618.
Yeah. Because only the mean value, there was a difference between the mean value. So now the mean value is become 2.5. So 2.5 kilonewton. Now what is the reliability index? Beta is coming from this case.
It
2.5
is
by,
0.96.
huh?
.969.
0.969. Okay. 0.969. That means it's a quite unreasonable value. That means we will get, if we calculate the probability of failure, just calculate the probability of failure. Phi of
Yes.
minus beta. How much is coming? Phi of this value.
Phi of minus 0.969. Uh, that
Minus
is
69.
0.166.
Yeah. Probability of failure is given as 0.166. Okay. So the beta value here is this. But Sovik, are you there? Sovik?
Yes.
So please check these questions, right? Make a
Okay.
note.
And mu c value is 35.
Mu c value is, yeah, mu c value is 35. It's okay. But here, what is the problem is here is that mu p1 is 31 and mu p2 is given as 20, right? So
Yes.
during this calculation, the mu p1 value is taken as 20 and this is taken as 30. And
Yes. Yes.
this will lead to the answer this,
Hmm.
this. So this cannot be the answer of the question, right?
Yes. Yes.
Okay. So make a note. Okay.
Okay.
Okay. So Abul, I think this is in your question, right?
Yeah, it is the last assignment question.
Last one. So there is a little misconfusion regarding that relation. So for now, you just go with that range here, the coming as this. But we will, eventually correct this question or drop it.
So, so basically, when I answer that question,
Yeah, you
which
answered this question. Okay. If you
like,
have this value 0.969, you can
mhm.
directly put it here. I hope this value will not be there. You will get some range about this. So just go for this value.
No, no, actually, this question has is it it is open choiced. It is fill in the blank.
Okay,
So
okay.
I'll have to type it.
You have to type it, right? But
3 points.
I hope for the answer, yeah, you just write the correct answer. We will later on change it. Okay.
Thank
The
you.
okay, okay. I hope that 2.94 to 2 point something range will be that range given to that question. So that question will eventually be dropped. Okay, no problem. Okay, just you fill the right answer and we will do the next. Fill in the blanks. Why I'm concerning about it? Like I hope that the range of the right answer is given to 2.9 to 2 point that. If you feel that right answer is this, that question that the answer will show that okay, this is the
Actually,
wrong answer.
sorry to interrupt you. The question is same,
Yeah,
but we have to answer it like we have to type it down there.
yeah,
It
yeah,
is meant to round off to two decimal places
yeah.
and type the answer. So there are no options for this question.
Okay, okay. Just type the answers. There will be no issue. Okay,
Okay.
okay. So let's quickly solve another problem. Here we have a simply supported beam of length L, 4 meter is given. Now you also check this question also. 4 meter, section of 100 mm multiplied by 150 mm made up of steel. Great. So we have a beam, simply supported beam. Whose length is like 4 meter is given. Say let's we have a beam and the cross section of the beam is also given. So B is like 100 mm and D is 150 mm. Now that says that E, that means Young's modulus, is follows normal distribution with mean this and standard deviation this, and a UDL is applied over or throughout the beam, where that W follows normal distribution. Calculate the reliability index using MVFOSM against the limit state of 10 displacement. Considering the limit state equation is in this format. Now tell me how we can solve it. Limit state of deflection. So we need to consider the maximum deflection for the UDL first. So here what we have, a simply supported beam with UDL, we have some length. So what will be the maximum deflection occurring at the center point? Del is nothing but 5 WL to the power 4 by 384 EI. Yes, there is no doubt. Okay.
Yes.
So from this sectional properties, we can find it out the area moment of inertia BD cube by 12. So
Mhm.
this come as this. Now, what is this? That del maximum allowable deflection.
At
This
the
is
center.
huh,
At the center, deflection at the center.
at the center. That means that will dictate the demand.
Yeah.
Like maximum deflection will be your demand. Now,
Mhm.
what will be the capacity? For the capacity already given in the question,
Mhm.
10 displacement, right? So
Mhm.
that means 0.1 meter. Now you can formulate the limit state function. G is equals to nothing but this is your capacity 0.01 minus your demand.
True.
So simplify the equation and tell me you are getting that 2.88 or not. Just do the calculation, please.
Okay. I do. Into 12.
And simultaneously, I also do it.
10 raised power 8. 5. 8. Getting a different 0. Getting the same value.
You are getting the same value. So then, okay, we can proceed with that. Okay, this is our mean value of the limit state function. Clear?
Yeah.
Now we need to find out the standard deviation. Are they correlated? Are they correlated? No. So it will be a simple expression for the standard deviation. It's you just need to find out the uh, derivations with respect to W and derivation with respect to E. So 5 WLQ. So here the derivation is simple, 5 L to the power 4 by 384 EI. Just put all the value and check. Is it the correct answer? And this is the correct answer or not. All the values are there. Now once we you know uh, get to the point where we can conclude that this okay, so the answer will be okay. We just put the answer value. Simultaneously, I also checking it. Is it correct or not? Cross checking it. 0.005 meter.
Same
Same, yeah, coming
for
as
both.
okay. So now we can have the values over here. This is our the value of this derivation, and we have already variance of W. That means variance of the deflection at the midpoint. That is also given as 2.5. Okay, so 2.5 square. Great. Now this is the derivation with respect to the Young's modulus. The value comes as 3.55 into 10 to the power minus 11. Just square of it, and variance is again 2.5 into 10 to the power 6. Now why 2.5 into 10 to the power 6? I think the values are given in GPA. So from GPA to we have converted to MPa.
Yeah.
Okay. So are you getting the sigma g value as 1.48? Just check it once. make all the calculation, just put it in your calci this equation whole. I think all the values are here correct. Yeah, this value is coming 2.22, 2.25. Yeah, under root of.
It's coming the same.
Yeah. Same, that means the reliability index we can easily calculate this. Now probability of failure also we can calculate if we need to further extend it. So phi of minus 1.946. So we can easily calculate. Like what will be the value of phi here? That value. Just calculate it. Minus 1.946. 0.025, right?
Yeah.
Okay, great. So now let's quickly next problem. What we have next problem? Okay, this problem is directly taken from the video lecture. You can go through it and easily find it out. The value of reliability. So you have that limit state function over here. Again, what you need to do, find out the mu s from the limit state function and sigma s from the limit state function. Once you get the two value here, what the question says, you need to find out the reliability against a capacity of this value. That means if we plot it here, this is that plot. So up to this point, you will get the reliability. And beyond the point 4.75 MPa, you will get the failure points. So what you need to do? You need to just integrate this PDF up to the value this. That means directly you can get it from the standard normal table, that this is your target value minus the MS value divided by sigma is 1, and you will directly get the reliability from here, right? So basically, till now what we have solved that how to get the probability of failure. So we have seen that we can have the probability of failure if we have the non-dimensional number whom we call the Cornell's reliability index, and this is defined as the mean of the limit state divided by the standard deviation of the limit state. And the limit state actually we have defined like capacity minus demand. Now, in all the questions, you have seen that the question says that you should follow this format for your limit state. Now, if you don't follow this format for your limit state, what will happen? We will see. And this we address as lack of invariance problem. Now, why this lack of invariance problem? I will tell you in a minute. First, check what we actually call the lack of invariance problem, right? So let's say we have the limit state in that format, c minus t. Now, if I change the format like this, that g of x is equals to 1 minus d by c. That means I've just divide this c from here. So I can write that my g of x, I can write either 1 minus d by c or c by d minus 1 equals to 0. These three formats. Problem will be same, but the formation of the limit state is different. Now, if we change the format of the limit state, that means our problem is same. We just change the format of the limit state. Now, intuitively, what comes into our mind that the reliability index should be same for two cases. Let's see, is it the case we are getting the reliability index in same manner, or is the reliability index is changing or not? So let's quickly go to two of the important example. Like we already have solved this problem, right? Where we have considered the limit state as this format c minus d, and we have seen that the beta value is coming as 3.9712. We have checked the calculation on all this. We just have solved this problem, yes or no? Now, if we change the limit state format of the limit state, right? Now I want to, formulate the limit state like 1 minus d by c. Now let's see what will happen. Now if we change the limit state again, so again we have that random variable associated with demand and capacity, and our limit state function was to respect to your limit state of serviceability. That means 1 minus we will have 325 PL square by 3L. So if you solve this problem, so Gx will be nothing but 1 minus that value. So if we simplify, we will get the mu value. Then again, you need to differentiate with respect to the variables, because we have here three variables, P, L, and E. So we will have three differentiation with respect to the limit state function, and the values are this. You can cross check it, but first, we will come to the conclusion that what we call the lack of invariance problem, or we come to know what we call. So by this way, we can easily find out the value of the variance, right? Here, sigma g square, and that comes as this. Now, if you put all these values, you will find that beta is coming as 3.6412. And on the previous problem, we have seen that beta was coming as 3.9773. First problem, for the solving the first problem, we considered this, that means limit state as capacity minus demand. Now for the second case, what we have changed here, just format of the limit state. We just use Gx as equals to 1 minus d by c instead of capacity minus demand. Now that will give you the value of beta as 3.64. And obviously, if your beta will change, eventually your probability of failure will change. Probability of failure will change. Now this phenomena, like if we change the format of the limit state, but the problem is same. For both the cases, we define the limit state with respect to the serviceable limit state criteria, where the serviceable limit is given as L by 325. The problem is same, the random variable is same, but for two cases we'll have two reliability index and two probability of failure criteria. Now this phenomena is called lack of invariance problem. Now why that lack of invariance problem is arising, that is just because of, just recall, we will solve this problem too in a minute. Just recall that we have derived first thing we have, when we have formulate the mean value first order second moment method. See what we have done, we actually first truncate that series at second order. I come to it. First we have taken the mean as a reference point. Where is the slide? Yeah, we have considered the mean as a reference point. But for all the cases, it is not necessary that mean will be your reference point. The reference point or the reference design point will change. We'll see when we will solve the second order reliability method using, or the first order reliability method using Requis-Fissler algorithm for nonlinear functions. Then we'll see that that value will change. The design point, we need to find out the optimal design points. So first thing. Second thing, here we have truncated the series up to the first order term. So due to that two reasons, some error will occur, and that cumulative error will show, in the final results when we change this format. So, that means we cannot rely on the MVFOSM for, you know, uh, method to solve all the reliability or complex reliability problem. We need to have some more accurate methodology, so which we will see, like first order reliability method solving using Requis algorithm, and that Cornell's reliability index actually we will see as a Hasofer-Lind reliability index, where that lack of invariance problem will solve. Like if we use any kind of format for the limit state, that will give us that same end result. Okay, so like let's solve one problem, then we will move to Hasofer-Lind reliability problem. Let's solve one example. Now, no, that thing is, I hope, clear. What is that lack of invariance problem and why this is arising? Clear? Due to the assumptions whatever we made to get that two moments, right? Nothing else. Now your task is to verify these problems, are the calculations are correct or not. If not, immediately report me. You have my mail ID, so mail me. I will immediately reply that okay, and do the necessary corrections if there is any. Now let's quickly solve one problem regarding that MVFOSM problem. Like, okay, we have a here, just see the problem. Consider a steel beam carrying a deterministic bending moment. Okay, cantilever beam, one bending moment at the free end is there, and this is a deterministic quantity. Deterministic, that means only it has the mean value, right? This is the mean value of this. No standard deviation is there. Now the sectional modulus Z and the yield strength Fy are statistically independent, and they are following the distribution with mean this and standard deviation this. This one is for your Fy, and for Z with mean 54 and sigma 20 to 2.7. So first, uh, we will solve for two cases, normal and log normal. Now we make two case study, like if we use that normal and log normal, two different variable in within our function, so how much it will change, and also to address the or to check the lack of invariance problem, to quantify the lack of invariance problem. So first, what that says, key first you need to formulate the gx for the plastic moment carrying capacity of the beam. Plastic moment carrying capacity of the beam. Okay. So for normal case, first we will solve for the normal case. So what will be the gx? Gx capacity, what will be the capacity? Fy into z, flexural moment resisting capacity due to the moment, and what will be the demand? The applied moment, m. It's very simple. So we have the gx over here. Now you can calculate the that mu g and sigma g. Now calculate it and tell me the values, please. What is the value for mu g and sigma g? So here what I have done here, I have separated out c and d and make the calculation separately. Now if you solve that directly from this expression, are you getting the values same as this or not? Just it will take just 2 minutes. Just do the calculation.
Mu G is coming out to be 912.
Mu g is coming as
1 2.
912 kips inch. Okay, and sigma g,
I'll have to do it.
you just need to make the differentiation, right? With respect to Fy, with respect to Z, and you with respect to, yeah, 2. Moment is the deterministic quantity here. Now here I have, simplified the equations or simplified the calculation actually. I just, put the capacity part here, and then demand part here, because the demand is your deterministic quantity. That why I separated out, so that the calculation will easily I can calculate it, or that will require more time, less time, sorry. Just tell me the beta is coming as 3.97 or not.
4.00.
4.00.
Yeah.
4.00, yeah, it's nearly same as 3.97.
Okay.
So you can check this way also, you will get same value, like 4.00 and 3.97 is similarly, like if you have considered 0.0003 third order or second order term, that will nullify. So we are getting the close results, and we can conclude that okay, our Estimation is okay. Now for the normal case, if we change the limit state, like here we are considering the limit state with respect to the plastic moment carrying capacity. Now just change it to this format, stress formulation. That means Fy minus m by z. We can do it. Just divided by z, we will have Fy minus m by z. So Fy, that will give the stress, and m by z, that will induce bending stress due to your m. Now if we have this format, just check it out, what will be the beta coming for this case, and give me the value. So what will be the mu g? First calculate mu g for the case. That means mu c minus mu d, and here you have mu of Fy minus mu of m by mu of z. Just make the calculation and tell me what is the value of mu g coming. Or you can directly use that format also for C and D, and then finally you can combine them and get the beta value from here, as you wish, but check the calculation please.
Mu G is 16.89.
16.89, 16.89, and I have getting as 38. You are getting as 16.89. Now let me check what I am getting here from this equation. 38 minus 21.11. Yeah, 16.89. Very good. Now, what will be the value of sigma g? You just need to make one differentiation here. What is the value of sigma g? Only you will have the differentiation with respect to z. That will give you some considerable value. With respect to Fy, it become to 1. So only you will have to differentiate this part only. So how much is the value is coming? Is it coming as 3.944 or not? So what you need to do here, well, you just need to differentiate once. dg of x by d of fy, that will give you 1, and del g of x upon del z, that will give you that value, m by z square, right? Minus of that, and if you whole square that, it will give you the value of m by mu z square. Now are you getting the value 3.944? Just confirm it. Abdul, are you getting it?
No, my answer is not. I'm making a mistake, I believe. I'm actually trying to write it down now.
Oh, okay, okay. We do it. It will get just 2 minutes. Just get it done, and just verify the answer so that we can proceed further. Okay. Uh, I have checked it. It is coming as 4.28. You just check it. Like your mu g, same as my mu g, 16.89. Just you need to find out that sigma g value. So I have 1 square multiplied by mu sigma fy square, plus you will have sigma z multiplied by m by mu z square, and that will lead to the final answer. Okay, leave it for you. You just check it and verify it. So what actually we are trying to say here is, if we change the format of the limit state, here we have the limit state in that format where we get the value of beta as 3.97 or nearly equals to 4, and for this case we are considering the normal case only, we are getting 4.28 value. That means today we have learned how we can find out the probability of failure using variance of algebra and Taylor series expansion, and we call this method as first moment a mean value first moment second first order second moment method, mean value first order second moment method, because we have already seen that we truncate the series at first order, we take the reference point as mean for the Taylor series expansion and all this, and we have seen that the beta value and simultaneously the probability of failure will change if we change the format of the limit state, and this problem is called the lack of invariance problem. Now here my question is, like, if you have given the problem either this or this one, now if the limit state format is not given, you will not find out the desired probability of failure, or for the different cases you will get the different probability of failure. That means we cannot wholly rely on the MVFOSM process. We need to find out some more reliable methods to find out the reliability and probability of failure. So, what today we have learned one method about the reliability, to find out the reliability index, whom we call that Cornell's reliability index, and then we find out the probability of failure, and we have solved few problem regarding this. So now, to address this lack of invariance problem, actually the Hasofer-Lind reliability index come into play. Now actually what I have planned, that Hasofer-Lind reliability index and the first order reliability method for Requis-Fessler algorithm, you know on the next class I will fully dedicated to that Hasofer-Lind reliability index and first order reliability method. We will solve that Requis algorithm, you know uh, we will code it, and we will solve problems related to form correlated, form uncorrelated, and different, like if we need to convert this into standard normal space or not, we will solve this type of problem. So today we will not start this topic, but for example, like for two or three things I want to mention here. Like if we have a limit state on the normal, that is from definition of the limit state we know it's capacity and demand. Now if we transform it into standard normal space, what will happen? Nothing but, in standard normal space what we do, we just subtract the mean from that random variable and divide it with that standard deviation. So z1 and z2 we will get from here. Now if we put that z1 and z2 value in my you know limit state function. So capacity, now we have capacity is equals to what, I can write capacity is equals to z1 sigma c plus what I can write mu c, and what is d here, z2 sigma d plus mu d. Now put all these values in your that format, c minus d value, what you will get, this is your limit state in standard normal space. Now, Hasofer-Lind reliability index and the first order reliability method using Requis algorithm deals all the limit state in standard normal space. That means first we need to convert the limit state into standard normal space. How we can convert the limit state into standard normal space? Just this is the process already we have seen, that just subtract the random variable with mean and divide it with standard normal space. So in a question, if asked that limit state is given as like uh, x1 minus 2x2 is equals to 0, and the x1 and x2 values are provided in the normal space, and the question asks find out the limit state in a standard normal space, what will you need to do? You just need to convert these variables into standard normal space, and then you need to put all these values in g of x equals to c minus t format. You will find out the value of or the expression for the limit state in standard normal space. Clear? I hope this week assignments will not cover the first order reliability method using Recruit's algorithm, because Recruit's algorithm will take itself 2 hours to elaborate how to solve the Recruit's algorithm step by step, how we can solve them in pen and paper and get the first 2 iteration, and then we will solve the Recruit's algorithm, or we will code the Recruit's algorithm in MATLAB and we will solve the problem. We will see that how to calculate the find out, you know, beta and probability of failure at the same time. So today we will not touch upon that uh, thing, but yeah, on the next class we will dedicate it to that thing. So I will suggest that on the next class you should be with your MATLAB, so that we can, you know, code simultaneously and you can see what are the steps and how we can incorporate these things using first order reliability method and how we can solve it. We will solve different kind of problems, like these all are explicit form of limit state. Now if we have the implicit form of limit state, how to deal with that? So all these things will be covered. So till now you have any doubts, you can ask me. I think one or two question like came from this, you just need to convert the limit state into standard normal state. So like what that Hasofer-Lind reliability index says, it's nothing but, you know, first you have the limit state in normal space, you convert it into standard normal space. Now the sorted distance from the origin to the standard normal space is called the Hasofer-Lind reliability index. So we will see on the next class. Today we will not touch upon this. So till now, do you have any doubt? Yeah, Bob.
Hello, good morning.
Yeah, good afternoon.
Uh, Good afternoon. I want to suggest, is it possible to move the class to 6 p.m.? Is it
Is
possible?
actually it's not possible to shift that
Okay.
6 p.m. because actually that NPTEL team will send you some mails regarding that, so they need to change from their end, like uh, that what that process, you know.
So, so it means I can suggest to NPTEL.
Yeah, I need to talk to NPTEL that if it is possible to shift from 5 to 4 to 5, or other slots. I hope, you know, mid of the courses these shifts generally don't happen. Okay, so you need to what is your problem, like I want to know.
Mostly on Sundays, I'll be at church from that time. Ghana time, that time is just 9:30. The time you start. And most of us in West Africa and other part of the GMT, most of the time we are in service.
Okay,
So
okay.
it makes it very difficult to join. This time I even have to sneak out of church to come.
Yeah, and already when you have joined, already we have solved the problem which were important for your assignments as well as the
Assignment.
concepts. Yeah, as the concepts we have covered.
So
Like till now we just
are you going to upload it today? Are you going to upload it today?
yeah, I'm going to upload it today. But
Okay, okay, then I can go through.
it's my suggestion, try to join and solve the problems and queries so that you will get the clear answer. Like, okay, I may wrong, the problem which we will solving may wrong, but if we discuss and solve simultaneously, okay, we will conclude this is right and this is thing. And here, like for now we just, you know, solving the statistics and all these parts. When we will actually code the things, then it is important to have the interaction session, otherwise you will get the recording video. But if you have any questions, like I have calling a function file from here to here, how I get that function file, how I formulate this function file, why this function file is there, why I am not writing the code like this, many questions will arise, right? So
Oh,
that,
I agree with you perfectly. It's just that it's a bit difficult for me, very, very difficult for me to join at that time because I mean that's our normal day of time of worship, and it's difficult. But I
yeah,
think I'll see what I can do.
I can understand. I will talk to NPTEL team if possible, like instead of 3 you are saying that can we have it from 4?
Uh, I mean, from normally six your time 6 o'clock is your time, right? Like if
No,
you can have
India time, I think it's 3 to 5 p.m.
yes, but 6 o'clock at your end is 12:30 here. That is when we have almost or every church would have finished complete. But if I know you can, if you can shave it a little, that is fine. If you cannot, then it's I'll manage with it.
Okay, so like yeah, I have what I have come to know that three or four of you have registered for the examination, so we can have it when you people are comfortable with that. Like we just have the sessions like fully interactive. You and
Yeah, it's very, very, very important because the interaction I don't want to miss, but when it comes to this, I don't know what to do.
yeah. So
So
where are you from? Actually, Abdul,
I'm
I
from
think that
I'm from Ghana, West Africa.
okay. From where? Ghana.
Ghana, West Africa.
Okay, 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 okay. Okay, I will talk to them, but I think they will not change the slots because all the slots for the NPTELs are already been decided, and one auto-generated mail is already passed on. Still, if it is possible, I will you know write
Okay.
a mail to them. But you will have the recording videos on that session, and if still if you have any kind of doubts, you can directly mail to me. I will
Yes, 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 yes. Thank you. My number two is how do I get the MATLAB software? I've been looking for it. I don't know how to get it.
Okay, so first thing, for this course, if you want the MATLAB from this course, I think the MATLAB is inbuilt with that course. You write to mail to that NPTEL support team, they will provide you the MATLAB, and this will be activated for these sessions. And if you want that MATLAB, like just download the student version or just download the crack version, man. Like you will get it in. I cannot say online, but
No,
you
I
can.
understand. I understand you. No, I get the point. Don't worry. Don't put yourself in trouble. I know what you're talking
So,
about.
so
I
what
think
I
I will.
can, what I can do, I can share one drive link where MATLAB 24 and 22 is there. So you can directly download from there and you can use the crack version. Okay.
I will be very, very, very happy to see that. Very, very, very happy
So
because I.
just share your mail ID. I will give it to you. 2028 and 2024 already I have there the crack version. You just can do it. Or the most easy solution is just download the student version. It will do the same. Okay.
Okay, I will send you an email. And I will send you an
Yeah.
email.
You just send me an email that I am regarding your like just send me mail. I will share that drive link where that MATLAB is uploaded and how you can download this and install it. All the instruction I will share with you. No problem.
Thank you very much. Thank you very much.
Okay.
Your name is Devices?
Yeah, my name is Devashish Kumar. Thank you.
Okay, I just wanted to know whether I pronounce it well.
Yeah, Devashish.
Okay, all right, that's good. Thank you very much.
So, Abdul, do you have any queries? I hope the timing will not change. Okay, they will. On the previous semester, I did that Java and infrastructure course, but still,
No, I don't have any questions. Thank you. A lot of confusions got solved today. Thank you.
okay, 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 okay. Thank you. But still, confusion will arise on the next class and onward when you will solve actually the reliability problem. So,
Yeah.
please do join on the next session and make it more interactive. Like be with your MATLAB. I will provide the MATLAB also, no problem.
I'm
Okay.
actually working in reliability analysis right now, so I
Oh,
have to release this. Okay.
so Abdul, you are from where?
IIT Hyderabad.
IT Hyderabad. So
MRF.
you are PhD or MTech student?
PhD PMRF.
Okay, you are also a PMRS student.
Yes.
So yeah, I am also one.
Yeah.
So yeah, actually I was the one of the TA of this course. So I have while preparing that things I was there as a lead TA. So I have the codes and that algorithms which will be required for like you are working on reliability which part
Uh,
reliability analysis of
I'm actually working in geotechnical aspects, so slope stabilities.
yeah sub stabilities you can easily incorporate the first order reliability method or the simulation based technique easily you can
We've been using FORM and SORM, but I'm facing some issues in simulating it right now. So I
okay
will just rectify my codes by these sessions,
Yeah,
inshallah.
you can discuss with your problem, like what is the problem, how we can formulate it, like for the implicit, also implicit functions, like here what we have seen today, all the limit state what we have encountered today are in a explicit form, yes or no?
Yeah,
All are in explicit form. Now we will solve also that implicit limit state. If we have implicit one, like if we have a building, 10-story building, or a bridge, or your foundation part where the soil structure interaction is happening.
yeah.
So if we have like that, so we will have implicit kind of limit state. So how we can incorporate the first order reliability method to solve that implicit kind of limit state method, we will also solve. And I will also give the if necessary the codes, like what we will get in implicit limit state. You just need to get that you know demand part and capacity part from a simulation code, like from
Okay.
NCs, from mechanical APDL, from SAP. So we will automate that software into MATLAB and we will perform that reliability analysis. So with the due of the course, we will see. I think week 11 and week 12, Ornasis sir has already showed you how to incorporate mm, that implicit form in the reliability with structural design. So I will show that course to you, and it's you know uh, quite rich in mathematics and coding part, so it will help you. I hope it will help you. Like if we have a model, and if you can model it with NCs, and for one variable you need to incorporate the randomness, you can use that formula and that algorithm to automate that thing, that from that software you will getting the value of capacity or demand, and from this you will perform the reliability. That means MATLAB and some other software, like I prefer the NCs. Yeah,
Uh,
mechanical APDL we can
that
incorporate.
would be great. That would be great. That would be great.
And you are in cycle 11.
Cycle 11, yeah. Cycle
Yeah,
11.
so cycle 11. Okay. So I was
Unlucky
like,
cycle, the last cycle.
yeah, and me from cycle 10.
Uh-huh. Okay. Okay, fine. I'll contact you through
Yeah,
emails.
yeah, no problem. So today we will stop here, and next class we will meet again. Okay.
Thank you.
So
Thank you.
thank you everyone.
Thank you very much.
Thank you. And you, Bob, please mail me, and I will provide you that
Yes.
software and necessary codes. Whatever you need, it's
Oh,
mail to me. Okay.
all right. All right.
Thank
All
you.
right. Thank you very much. I appreciate it.
Thank you.